Hey guys, it's IDW, and today we're going to be talking about branching. Now, branching is something that is extremely important in computers, and it's something that is so important that it's actually come up in a few things we've already discussed, even though it's not the exact topic of conversation. And it's just really important, so it's tied into a whole bunch of things in computers, which is why it's come up so many times in memory and such. Anyways, so diving right into things. Usually, when you're coding, you go through it in a specific order. You'll do instruction A, instruction B, and then instruction C. And usually this is just fine, but sometimes you have a problem where you don't want to do this. For instance, let's say that you want to do one set of code if one value is greater than another, and you want to do a different set of code if the first number is less than the second number. So then the computer has to make a choice, and it's these choices where we get into the concept of branching. So when a computer goes out of order from its normal order, a branch occurs, and branches are an extremely important part of programming, and at the same time they are the slowest function in the entire computer. So now, in order to understand branching, we're going to have to understand Boolean logic, and a Boolean logic is basically just logic based off of true or false stuff. If in the condition of true, then you would be actually doing something. In the condition of false, you would not be doing something. Anyways, when a computer comes across a problem involving going into code out of order, it asks its flags what to do about the situation. And flags are basically booleans, or true or false logic, in one specific CPU. For instance, one CPU's flags might be its carryout, and the significance of that would be that if the carryout is on, then I might want to go to one set of code, whereas if it's off, I want to go to another set of code, and you can see how that's useful. Anyways, so once again, when you go out of order like this, it's called a branch, and branching itself is an instruction. Separate branch instructions are assigned to different flags. That's not usually what happens, but it's what happens in our computer. So the branching condition is the specific flag that's being used in a situation. And the term for the specific flag that is used in a branch is the branching condition. So if you've ever heard of conditional branching or conditional goto, that's exactly what people are talking about when they say this. So yeah. And in our CPU, the branching instruction comes from the previous clock cycle, and that's just so that we don't have to be doing a function and testing our flags at the same time. So yeah. So what exactly is branchful useful for? As I've said, it is extremely useful. So we're going to see it come up all over the place in programming. If you've ever programmed a computer, you've used branching, just period. If you used a loop, if you used a logic statement, or if then else, or functions, or as they're sometimes called, methods, these all use branching commands where they go out of order. Loop, when you reach the end of the loop, you branch to the start of the loop. When you're using a logic statement, then you'll branch to one place depending on the condition, and a different place depending on the other condition. And using a function, what you're going to do is you're going to have a certain set of code, and you're going to branch to that set of code whenever you want to use it for an operation. Anyways, it's very good software form to have in branching functions. It's not absolutely necessary, but if you want someone else to look at your code, it's really important that you show this, and yeah. So it's really important for this if anyone else is ever going to read your code. So if you've ever wondered why you do that when you're programming, that's why, because it's easier for other people to see. Anyways, now we're going to get into the giant mess of branch prediction. Now, if you remember, earlier I said branching is the single slowest function in a computer, and the reason for this is that it actually interferes with a pipeline that computers use to make themselves a little bit faster, and the way that that basically works is that the program counter doesn't have to rely on any other part of the computer, usually. So the slowest time for a clock cycle would be the amount of time that it takes information to come from memory and to be saved back to memory. But with branching, it's the amount of time it takes for information to come from memory into the registers and then go straight into the program counter. And because of this, it interferes with the pipeline. So yeah. Anyways, as a result, modern computers actually try to speed up this process by guessing what the branching conditions result is going to be. And usually, what you'll do is you'll have like a queue or a stack of what your most recent branching commands were. And the one that's more frequent is the one you decide, and yeah. But now we get into the really messy thing about this. What happens if you go the wrong way? Now, thankfully in the computer we're building with Redstone, we are not going to worry about this, but branch mix prediction is an extremely common thing that comes up in computers all the time. In fact, the computer you're watching on this almost undoubtedly just made a branch misprediction. Anyways, what happens when your computer makes a branch misprediction? And the answer is that it does something called stalling. And stalling is basically where a CPU uncorrupts itself. Because when you actually have one of these cases where you have branch misprediction, your CPU, all the information that it could have manipulated in the time for it to find out that it did the wrong thing, all of that is pretty much contaminated, and it has to undo any instructions that it's done since then to get back on track really quickly. And when a CPU does this, it's pretty much useless, and so it's called stalling. If you do a Redstone CPU like this, you might want to have an indication light to tell the user if the CPU is stalling. So yeah. Anyways, modern computers stall all the time, but there's two reasons why it doesn't really show. First of all, it has to do with there are billions of clock cycles every second in modern computers, and they're lightning fast. So it's really hard to make it so that it's going to have much impact on the clock speed. But the next thing is that modern computers have more than one core, thank goodness, and this makes it so that it's really easy for, if one core goes bad and starts stalling, another core can just start doing what it did. So yeah, that's why we don't really notice anything in terms of stalling in our computers. If you're thinking freezing is related to this, it's usually not, but it can be, so yeah. Now let's talk about the computer we're making in Minecraft. So our computer is going to have 3 different branching commands. Branch unconditionally, which is basically it just branches all the time. Branch if there's a carryout or shift overflow. Those are sort of the same thing, not really, but close enough that we're going to call them the same thing. And branching if there is a shift underflow. So with all that out of the way, that's basically all that we really need to know about branching, the times that it's going to happen. Also, we're not going to have branch misprediction, as I talked about earlier. Stuff just gets messy and you need all sorts of different extra hardware in case you have to stall. And yeah, it's just really tedious. And branching is going to be the slowest function in the entire computer, which means it's going to determine the clock speed, which is actually pretty interesting. Anyways, as I said earlier, the way that our computer is actually going to be branching is not the way that you usually do it. Usually, when you get a branching instruction, you have a certain part of your command that is basically set off to all the CPU flags. So if I have 4 flags, then I'm going to have 4 bits in the instruction that I send into the CPU. And those are going to basically say what the flags need to be if I want to branch. And this makes it so that you can, first of all, do different functions with all the different CPU flags. Like AND is really easy to do, but it also makes it so that you can see if more than one condition is actually applying in the CPU. So if you need to do that. That's technically AND too, but whatever. But anyways, so yeah, that's how you usually do this. We're not doing this because we're actually doing something rather special with our computer that has to do with branching, and a lot of things I've mentioned lately, but I haven't related stuff to. That's really cool. But anyways, other than that, our CPU just has opcodes that are assigned to different branch conditions, so yeah. That's just about it though, yeah, so. Oh yes, actually the mode bit in when we're using a branching command actually can't usually be used, and that is just because of the way our CPU is built. We can't take the mode of something to get an address out of memory to branch to, unfortunately. However, because this won't work if we do this, what we can actually do is we can use it to say if we want the inverse of the flag. So branch if not true. So yeah, that's something sort of special that you also usually wouldn't have, but yeah. But that is everything that we are going to talk about today, so yeah, everything you've ever wanted to know about branching as well. So I hope you guys have enjoyed, and I'll see you guys next time.